Hello, everybody. It's Mrs. Pound, and I'm back with more in Chapter 4.1 on forces and motion. So, our topic for today is motion in Section 412. Now, the objectives for this video are to define motion, analyze a system to determine net force, and compare speed, velocity, acceleration, and also to be able to calculate speed, velocity, and acceleration. So the first thing we need to talk about is net force. This is the total of all the forces acting on an object. And so here in the background, I have an airplane. And we all know that the force of gravity is acting on the airplane to pull it down. So that's one force acting on it. But it's flying, so there must be a force holding it up, and we call that force lift. There also might be force from the wind pushing on it, either on the front or the back of it. There's some air resistance, which is friction. So it's all of those forces added up together. Now, forces can be balanced or unbalanced, and a balanced force has a net force of zero. There is no change of motion in the system. Kind of like this spoon balance with the money and the potato, it will balance there and stay still. So an example of a picture you might see with this is I have a box and I have a person pushing on one side with a force of 10 newtons and a force on the other side of 10 newtons. And both people are pushing on either side. So those forces cancel out and the net force is zero and that box will not move. Now forces can also be unbalanced. An unbalanced force does not have a net force of zero, and motion can occur. So we have a very similar situation to the previous picture. And these pictures, you should be drawing these. I left enough space, and I think there's a box in your notes to draw these pictures. So go ahead and draw these in. So I have 10 newtons on one side, and the other person's pushing with 20 newtons. So because there's a larger force on this side, it's unbalanced, and there's a force of 10 newtons to the left. This box will move to the left because there's greater force coming from the right. Now, when we talk about motion, we need to talk about reference points. A reference point is a point against which the position of an object is measured. And motion occurs when an object changes position in relation to a reference point. I have a car driving in the background because how do you know you're in motion when you're in a car? You know you're in motion because you see, you have the reference point of the landscape of the trees, and you see that they're not staying in the same place. Well, you're moving, they're staying in the same place, but that's another interesting question, like which one is really moving? You could take two positions on that, but you can see that you are changing in relation to the reference point. And so that is what is going on. So another question is, what if both another car is next to that car and they're traveling at the same speed? We know that they're moving because of the landscape, but if we took the landscape away, they actually would not be able to tell that they are in motion. They would think that they were sitting still in relation to each other. They would only know that they were in motion if one started to fall behind or move ahead. Which comes to another interesting point. I imagine you're probably sitting in a chair. So are you in motion? Well, relative to the chair and the room around you, no, you are not in motion. But if you were to compare yourself to, say, the sun, you are in motion because you are attached to the earth that is going around the sun. So you have to always have a reference point when we talk about motion. Now, one thing we talk about with motion is speed, the rate at which an object moves. So we might say if a truck is traveling 32 kilometers per hour south and a car is behind it traveling 54 kilometers per hour in the same direction, what would be the speed of the impact? So thinking back to our force problem previously, would we add these together? Would we subtract them? How would we find the speed of the impact? I'll give you a second to think about that. Maybe pause your video and think about that question. We would actually subtract them. It would be 54 kilometers per hour minus 32 kilometers per hour equals 22 kilometers per hour. Their relative speed would be that. The impact would actually be 22 kilometers per hour. It would not be the full impact of both speeds. Now, if they were traveling head on, then we would add those speeds together. But if they're traveling together, we subtract them in the same direction, I should say, if they're traveling in the same direction. Now, the formula for speed that we're going to be using in class, and we're going to get some practice with this, is speed equals distance over time. And I abbreviated it over here on the right for you. So there is an abbreviated speed right here. Some units that we will use are kilometers per hour and meters per second, also miles per hour, but remember in science class we use metric. So a question might be, a train traveled 300 kilometers in 15 hours. What was its average speed? Well, remember the first thing we always write down is the formula. So write down S equals distance over time. Then we plug in the numbers. We have for our distance 300 kilometers and for our time 15 hours. We then divide 300 by 15 and we get 20 kilometers per hour. Now, the P for per replaces the division sign in this case. Sometimes we also talk about velocity. So what's the difference between speed and velocity? Velocity is the speed of an object in a particular direction. So for speed, we would just say 54 kilometers per hour. But if we're talking velocity, we have to add the direction of south. Or we would say 2 meters per second up for velocity. So we always have to add a direction. That's why I have the windsock in the background, because with wind can have a speed, but it also has a direction. So that would make it velocity. Another quantity we talk about with motion is acceleration. This is the rate of change in velocity over time. So this is when three things will happen: speed up, slow down, or change direction. These are all types of acceleration. There's a formula for acceleration, and this looks pretty complex, but it's actually relatively simple. Acceleration is the final velocity minus the initial velocity over the final time minus the initial time. And a lot of times the initial velocity and the initial time may be zero, which would simplify this even further. So an example of an acceleration problem is a car takes 10 seconds to increase its velocity from 10 kilometers per hour east to 40 kilometers per hour east. What is its acceleration in meters per second squared? Well, always write down our equation first, so make sure you copy that down. And then we look at the problem and we see, what are we going to plug into this? Well, our final velocity is 40. That's what we end up going. So 40 kilometers per hour minus our initial velocity, they do give us an initial velocity of 10 kilometers per hour. Now our final time is 10 seconds, and our initial time, since none is given, is assumed to be zero. So these are the numbers that should appear. 40 kilometers per hour minus 10 kilometers per hour over 10 seconds minus 0 seconds. So let's do our subtraction on the top and the bottom to simplify this. And we simplify down to 30 kilometers per hour over 10 seconds. So we do our division. 30 divided by 10 is 3. So we have 3 kilometers per hour times a second. But look at this label. It doesn't match what they ask us for. They want it in meters per second squared, not kilometers per hour times second. So we must convert. So this, I attempted to do a line here. This is the line that we usually have in our bridge notation. Okay, this is the line. So I know that in 1 hour, I put hour on the top because it's on the bottom here, there are 60 minutes. So that's my first conversion factor, but I need to get to seconds. So I need another factor. I know that if I have minutes on the bottom, I have to put minutes on the top. In 1 minute, there are 60 seconds. I'm to seconds, so I can stop there with my time conversions. But now I need to get kilometers to meters. So I need another conversion factor. Kilometers is on the top here, so it has to be on the bottom here. I know that in 1 kilometer, there's 1,000 meters. And now I'm to the meters. All of my units have canceled out properly. I'm left with meters, excuse me. I'm left with meters over a second times a second. So when I simplify, I get 3,000 meters over 3,600 seconds squared. When I do the division, I get 0.83 meters per second squared. Now, this was a pretty complex problem, but I like it because it combines some things that we already learned. So our objectives today were to define motion, analyze a system to determine net force, and compare speed, velocity, and acceleration, and also to calculate speed, velocity, and acceleration. We will be practicing that last point more in class. So don't forget your 5 questions, and I will be back with more videos later.